Hi class. In this video I want to talk about the basics of taking derivatives of vectors or taking integrals of vectors. We're going to deal with this in much greater detail in class, but I want to go over some of the basic material that you would have seen in calculus. And the basic point is we can use the vector operations of scalar multiplication and vector algebra, addition and subtraction, to compute simple derivatives and integrals of vectors. So the prototypical example when we talk about derivatives is to talk about the derivatives of the position vector. Suppose we define a vector r of t. Here I've written it in a three-dimensional Cartesian coordinate system where r is the position of a particle in 3 dimensions. So it's parameterized by the x position as a function of time t, the y position as a function of time t, and the z position as a function of time t. We can define the instantaneous velocity, v, as the difference in position over a small change in time delta t divided by the scalar 1 over delta t, over the time difference delta t. So again, although this is the limit process is what encapsulates the calculus part of it, but the basic operations here are just vector algebra, the difference of the position at two different instances in time, and scalar multiplication by 1 over the time difference. If we take this limit, this just gives us dx dt I plus dy dt j plus dz dt k. That's the usual form that we know for the velocity vector. Similarly, if we take a second derivative, we can define the acceleration, the time rate of change of velocity, and that involves the second derivatives, d squared x by dt squared, d squared y by dt squared, and d squared z by dt squared. It's been crucial in this derivation that these basis vectors, I, j, and k, are constant vector fields that don't change direction or magnitude with position. And we'll see an example of how that can change in a different coordinate system on the next slide. Let's consider the same calculation, the calculation of the velocity and the acceleration, but let's do this in 2 dimensions in polar coordinates. So here's our 2-dimensional space, our Cartesian basic coordinates are x and y, but instead we're going to specify the position of the particle by its radial distance from the origin r and the angle theta with which this position vector makes with the x-axis. So we can define, it's convenient in polar coordinates to define unit vectors in the r hat and the theta hat direction. Now these depend on the position where the particle is. So if the particle is at this position here, r hat is a unit vector pointing radially outward from the origin toward where the particle is, and theta hat is perpendicular is a unit vector perpendicular to r hat in the direction of increasing theta. If you reflect for a moment about what r hat and theta hat are, we can rewrite those in terms of our usual basis vectors I hat and j hat through this relation. R hat is cosine theta I hat plus sine theta j hat. Theta hat is minus sine theta I hat plus cosine theta j hat. Now, the position r of t is just the radial distance r, little r of t without the vector, times the unit vector r hat. That gives us, if I take r hat, I multiply by the magnitude of the distance r, that just gives me the radial vector from the origin to where the position of the particle is. But notice that in this expression, r of t, the position vector, there's a t dependence both in how far the particle is away from the origin as well as the direction in which the r hat vector points, because r hat depends implicitly on where the particle is. It depends on the theta of the particle at that time. So now when we take the derivative of r with respect to t to compute the velocity, we get 2 terms. The derivative of the radial distance with respect to time times r hat plus r times the derivative of the r hat vector itself with respect to time. Well, dr hat dt is ddt of what we said r hat was, cosine theta I hat plus sine theta j hat, and theta depends implicitly on time. So using the chain rule for derivatives, we see this as minus theta dot times sine theta I hat plus theta dot times cosine theta j hat, which if you compare with the definition of the unit vector theta hat, is just plus theta dot times theta hat. So if I plug back into this expression, I get that the velocity is r dot times r hat plus theta dot r times theta hat. And if you think about this for a minute, r dot is just the radial velocity, the rate at which the distance from the origin is changing. And theta dot times r is the angular velocity. Theta dot is often called omega, and this is just r omega. If you have a chance, you should try going one step further and computing the acceleration, which is d squared r by dt squared. Using these same formula twice now, and now you'll also have to compute the derivative of theta hat with respect to time, you'll see that the acceleration has interesting radial and angular components. The radial component is r double dot minus r theta dot squared. This is just the radial acceleration that you might expect. This is the centripetal acceleration. R theta dot squared is r omega squared, and it points radially inward toward the origin. And these two expressions here, r theta double dot is just the angular acceleration. Theta double dot is sometimes called alpha, so that's r alpha. 2r dot theta dot is a different term. That's the Coriolis effect, Coriolis force, that relates the angular acceleration to the rate at which both the radial velocity and the angular velocity is changing. Finally, I want to talk about computing integrals involving vectors. This is something we'll talk about in much greater detail in class. I want to start with the simplest example, that of a line integral. The prototypical physics example of a line integral is suppose you have a particle which moves from point 1 to point 2 along some path, and it is acted on by some force, F, at each point along that path. The work done by the force on the particle going from position 1 to 2 is the integral from 1 to 2 of F dot dr. And how do we define that? We think about breaking up this path into lots of little steps, delta r, and we compute F dot delta r for each of these little steps, and we sum over all the steps. The calculus comes in the fact that we then take the limit where the number of steps goes to infinity. That changes the sum into an integral. Now, we can use all of the formula and the of kinematics that we derived on the last two transparencies to actually compute the work in terms of the kinetic energy, and it goes as follows. The work is the integral from position 1 to 2 of the force, which is just ma, and I've chosen to write the acceleration a as dv dt dotted into dr. Well, dr, if I divide by a dt, I can write this as dr dt times dt. This is just taking a vector, if you want this infinitesimal vector dr, dividing by the scalar dt and multiplying by that scalar dt. But now, this integral, which started out as a line integral, looks rather different. It's the integral of a scalar function. This scalar function is just m times dv dt times dr dt times dt. And remember, dv dt is a vector, dr dt is a vector, the dot product is actually a scalar, and dr dt is just the velocity itself, v. So this whole thing is the integral from 1 to 2 of m times dv dt dot v integrated over dt. This is just an ordinary integral of a scalar function. The scalar function happens to be the dot product of two vectors. That scalar function can be simplified. V dot dv dt, if we write it out in components, is vx dvx dt plus vy vy dt plus vz dvz dt, and each of these terms can be thought of as 1/2 of ddt of the corresponding component of velocity squared. If I look at vx squared, ddt of that using the product rule is 2 times vx times dvx dt, and that 1/2 cancels it, so I just get this first term. And the same is true for the other two terms. So v dot dv dt is actually 1/2 of ddt of v squared, v dotted into itself, since vx squared plus vy squared plus vz squared is just the magnitude squared of the velocity, or v dot v, or v squared. So this whole thing, the work, can be written as the integral from 1 to 2 of plugging in here m over 2 ddt of the quantity v squared with respect to t. But m over 2 is just a constant. This is an integral from 1 to 2 of the derivative with respect to time of this function v squared integrated with respect to time. So the fundamental theorem of calculus just tells us is that function evaluated at point 2 minus its value at point 1. So we get that the work done going from 1 to 2 by this external force is equal to the change in the kinetic energy of the particle, 1/2 mv2 squared minus 1/2 mv1 squared. This is known as the work energy theorem.